Hello, everybody. Thanks for joining us today for our webinar, Torque Q&A. My name is Nikki Chris. I'm the marketing manager here at Interface, and I'll be your hostess for today's webinar. If you have any questions, please type them into the Q&A chat field, and we'll be sure to address them during our Q&A after the initial presentation. Lots of Q&A going on today. Any technical questions regarding the GoToWebinar platform are also welcomed, and I will answer them via the chat function to the best of my abilities. We are recording today's webinar, and a link will be emailed to all those who registered, as well as additional materials, including slides and the answers to all the questions. A short survey should appear at the end of the event, only 5 questions, and it will also be emailed to all in attendance. Our presenter today is Mr. Keith Skidmore. He's a product manager here at Interface. We've also got Mr. Chris Delling, our regional manager in the Northeast, on hand to help answer questions. So with that, I'm going to go ahead and pass it over to Keith to begin our presentation.
Hello, everyone. We're just going to go right into the questions. We have one from Ken that says, how do you address unknown issues such as startup torque and unknown torque transient spikes? And is the safety factor sufficient to address these problems? Those are very good questions. A lot of times people are interested in measuring torque, and because of that, they don't actually know what the torque is. That's one of the things they're trying to find out or investigate, and so it can be a little tricky. But typically, startup torque and transient spikes are present and need to be considered. Startup torque can be minimized by a soft start on a motor or just controlling the startup. There's a lot of inertia in line. You have to be careful because either starting up or slowing down quickly can cause spikes that you don't want to allow to damage the torque sensor. And then transient spikes would be things that come down the line, say during testing due to gear mesh or pulses from an engine, anything like that. So basically, you have to make a guess. You have to remember that the torque sensor capacity should be selected so that the spikes and the startup torques and all of those things fall within the capacity. And so torque sensors always have a safe overload range, but that overload range should be reserved only for accidental use. So that's number one. Number two, torque sensors have usually limits on how high they can go as far as the measurement, and that may be quite a bit less than the actual safe overload. In many cases, it's 10 or 20% above capacity. So if this transducer is sized, say, around the average running torque and the spikes are going up above that, you can't actually necessarily even tell because they'll basically be exceeding the measuring range of the sensor electronics and the signal clips. You may not know it, so you have to be real careful to size the sensor appropriately. Basically, there can be estimates made using, say, the horsepower rating of a motor and the RPM. You can calculate torque from that, and that's typically considered as the average running torque, and you know there will be spikes around that. And then you can start to estimate what the spikes could be using things like a drive service factor if you have a, say, a gas engine driving the system or an electric motor. A gas engine will cause more sort of severe service factor than the electric motor, for example. And the same thing as what your load is. If your load is, say, some kind of a crusher or a gearbox with sand in it or something, you could imagine, or broken gear teeth, you can get considerably more load spikes than if it's a fan, for existence. So you look at the drive and the load and associate service factors with those, and then use those basically as multipliers on the average running torque. So in many cases, the average running torque might be, say, 1, and you end up multiplying that by 2 or 3 to come up with the peaks. We can get into more detail on that, except it's a little more detailed to go into now, so we can look at that offline possibly with specific examples. But starting conditions and peaks can be up to 10 times more than running torque in many cases, so it's very important to consider those. Next question. When designing a rotary torque transducer into an application, do you think the pedestal mount or the general purpose, I'd say floating mount torque transducer is the best approach? I typically start with a floating mount. Basically, the sensor should always be protected by appropriate couplings. On a pedestal or a foot mount application, there need to be double flex couplings at each end of the sensor. in the sensor is never intended to be used as a bearing block. So the danger with the pedestal mount or a foot mount sensor is some customers or applications may tend to want to use that as a bearing block, but you definitely don't want to wear the bearings out in the torque sensor. So if they're going to be bearing loads, you need to make sure they're taken by bearings that are intended for that purpose, such as pillow blocks or jack shafts, whatnot. Definitely do not want the sensor to act as your bearing in the system to, say, support the weight of a flywheel or something. So I guess back to the question, on a floating mount, you really cannot allow that, in that the floating mount doesn't allow any weight to be taken by the torque sensor shaft. If a single flex coupling on each side of the sensor floats in between the support bearings, and it's basically impossible to load up the bearings when done correctly. So I usually start with the floating mount, and it's a little less expensive too. The sensors are a little less expensive, and the couplings are a little less expensive as well. So usually start with that approach. In some cases, say a fixture, I'm going to break it down and say reinstall a test article over and over again. The floating mount can be a pain because every time you break that test connection, the sensor is allowed to flop or sag, and you don't have any support. So it might be in that case a pedestal or a foot mount is preferred, but usually we start talking about floating installations and then move to a foot if that ends up making more sense. The question is, I usually recommend shrink disc couplings over keyed couplings. Is this the right thing to do? I agree. We recommend shrink disc type couplings, which basically is any type of coupling that grips the shaft as opposed to a keyed connection. Most of the sensors that we sell actually do have smooth shafts, and the keyed shafts are an option. There's a couple of reasons for that. One is a gripping type coupling, or a shrink type coupling applies the torque evenly around the perimeter of the shaft as opposed to a point load at the key. Shrink disc couplings are zero backlash. If you have reciprocating or changing direction torque, is not allowed to slip at all. Where a key may be a little loose and you get some backlash. The way to combat that with a keyed coupling is to have an interference fit between the hub and the shaft, which is easy to do on installation. You can heat the hub up and slip it onto the shaft. Say easy. It's a lot easier to do that than it is to get them back apart. And so one of the problems with an interference fit hub with a keyed installation is they can be awful hard to get back apart. And some of the methods that people use in the field that are quite okay with standard shafts and hubs don't necessarily apply when you have a torque sensor in line. You can't put the torque sensor in a press, or you don't want to basically cool the torque sensor down or heat it up. So you have to be careful to protect the torque sensor from some of the methods that are used to remove keyed hubs. So all of those reasons we prefer shrink disc couplings. Shrink discs are secure, but when you loosen them up, they'll slide off easily as well. Next question, what is the best way? Okay.
Keith, it's Chris Delling. Just the other thing I would throw in here regarding keyed shafts and keyed couplings, one of the issues that a lot of users deal with, especially for applications where torque sensors are going to be in service for a long time, is a phenomenon known as corrosive fretting. And essentially what happens is due to the very minute amounts of movement or backlash that a keyed coupling will allow, over time the keyed shaft will actually be worn down along the edges of the keyways. And this can lead to a number of problems ranging from increased backlash in some cases to, in severe cases, actual coupling or shaft failures. So again, for the vast majority of applications, I agree that the shrink disc type coupling is a preferred way to go.
Good answer, Chris. I guess one last point on that is I've had some customers who don't really trust shrink discs because they can slip, and when torqued to their specification, they will not slip, but the specifications also require that there not be grease on the shafts be clean and that kind of thing. And in some cases, if there's a test specimen that wants to be changed in and out a lot, in practice, it may be you can't necessarily guarantee that technicians are always going to torque everything to spec and everything like that. So in some cases, the keyed coupling can allow, say, quicker or more assured assembly without slippage, but you have the trade-offs of that we've mentioned previously. Next question. What is the best way to measure shear, lateral forces applied to a flat plate that is used to measure vertical force, e.g. weight? I think this is more of a multi-axis question versus a torque question, but we can address it. Typically, if there's a shear force and you want to also measure the vertical force, you'd either have to do that with multiple sensors or with a sensor that combines those two measurements into one. I've shown a picture here of a 3-axis sensor that measures force in the z-axis, which would be the weight basically, and then also it measures x and y forces, which would be the shear forces. And that can be done with a single load cell, as shown here, or several of these types of load cells could be mounted under a plate, and then the loads can be applied to the plate surface. Whether you use one load cell or several in this type of application depends a lot on sort of the geometry of the test. So it's not necessarily better to do it one way or the other until you understand what the load points are. And with these type of sensors, we usually want to talk about, the geometry, as in if it's a shear force but it's applied, 2 foot off the surface, there's a lot more going on than if that same shear force is applied right at the surface. So we need to understand not only the magnitudes and the orientations of the loads, but the geometry of where they're applied. Hopefully that answered that question. Next, how can you tell the direction of rotation from the output voltage? That's a very good question. In fact, it comes up fairly frequently. The output of a torque sensor, just like a load cell or any strain gauge sensor, is going to very typically be bipolar, which means the output reverses polarity as you cross through zero in your measurement. That really has absolutely nothing to do with the direction of rotation. It really only has to do with the direction of the torque. So say if you're slowing down a rotating system, for example, the torque very well may reverse, and that'll happen before the system stops. And eventually the reverse torque will cause the system to stop and then start spinning in the opposite direction, but it definitely lags the actual direction in many cases. So you really can't tell at all the direction using the voltage, but many cases these torque sensors can have an encoder installed in them, and that encoder can be used to tell the direction of rotation. A single track encoder just pulses with rotation and gives you RPM, but a 2-track encoder, which most of our sensors are available with, can actually look at the 2 tracks relation to each other, and that can be used to determine the direction of rotation. So, good question.
Hey, Keith.
Yes.
Sorry to jump in again, but the one thing I would point out here is if you're dealing with, I guess you can kind of make an approximation, I guess, of the direction of rotation if you're running at what amounts to basically a steady state condition, because obviously the polarity of the output is going to be positive in one direction and negative in the opposite direction. Again, assuming you don't have the effects of inertia involved like you described. So I mean, the basic premise of the way the torque sensor works, you have a positive output with a clockwise torque applied, and a negative output with a counterclockwise torque applied. But again, you can't use that as a strict rule because of what you described.
Thank you, Chris.
Yep.
Do we have a follow-on question on this? All right, never mind. Moving on. The next question was, how do you go about minimizing slippage at the mounting locations for torque cells that measure in both directions? That relates a bit to the coupling discussion we had earlier. Also with flange-type torque sensors, the flanges can slip, and it's actually a big deal. It's not necessarily always considered, but it can really goof up the measurement, and it can wear out the hardware. So there's really 2 considerations. One is effect on measurement, and the 2 is wear, and they both need to be considered. I was talking about a shaft style sensor. I think we've already talked about interference fits with keys, or better yet, shrink disc type couplings that grip positively onto the shaft. If it's a flange type sensor, basically it's the friction between the mating flanges that prevents slippage. So it's not the bolts themselves, it's the bolt tension that creates the friction between the two mating surfaces. And so the friction surfaces have to be clean and dry, for example, and then the torque on the bolts has to be proper, and typically it's using grade 8 hardware and bolts torqued to spec. A lot of cases the mating friction really is maybe less than ideal, and so you have to maximize it by applying as much torque to the mounting hardware as possible. And so you definitely don't want to go on the low side of the torque spec. You'd want to go on the high side. Usually you can tell if there's slippage if you, say in calibration at least, you can look at the shape of the calibration curve, and if there's slippage, instead of a smooth curve, you get some irregularities and discontinuities as the torque is applied. In many cases, certain torque sensors on the market actually don't have enough clamping force, even if appropriate hardware is used. And that tends to be in the case where you have multiple capacities in the same package size. In that case, if you're going to have reciprocating torques, and say especially in a fatigue application or an application where you expect that there'll be a lot of changing direction, it's important to address that, and that can be addressed by either having a sensor that has more mounting holes at the same capacity, or on a bigger bolt circle, bigger bolt holes, or all of the above. And one example actually is a design of a flange sensor that's been around a long time. There are many companies making it at this point, but some of those sensors have, say, a little too much slippage at their higher capacities, and so we can do a sensor that basically has more holes. I can show you an example of something like that here. This is a sensor, basically our 5400 series, which drops in for sort of an industry standard package. But in some cases, like the 50K and the say 100K capacities, actually the 50K and the 100K capacity are in the same package. So the 100K capacity in that package tends to have that issue. And so this would be an example of that same sensor with an improved mounting configuration, basically with a lot more holes. So you can either have more holes, you can have bigger holes, or you can have them on a bigger bolt circle. And so those are things that can be done to prevent slippage. Back to the slideshow. Do you have any comments on that, Chris, before we move on? Nope. All right. Next question. Are there sensors available that can measure both applied load and torque simultaneous? Yes, they are. Typically, Interface calls those types of sensors axial torsion. In most cases, they are static or reaction type torque sensors in that they don't rotate, or they only rotate through limited range. The reason for that is typically if you have bearings, then you also have to allow the force to be transmitted through the bearing into the measuring section, which can be done, but it complicates things somewhat. Typically, an axial torsion sensor is a sensor that has two separate bridges. One bridge is applied to a section that's measuring torsion, and then there's another bridge that's wired and mated to the sensing section to measure thrust. These sensors, typically the ratio of torque to force is somewhat fixed by the geometry, and so you can't necessarily say I want say 10 inch-pounds torsion, I want 10,000 pounds thrust, and make a sensor to do that, because the 10,000 pounds thrust will basically ruin the 10 ounce or 10 inch-pound torsion section. So there are definitely compromises. As far as rotating sensors, we maybe talk about that offline. If somebody had a specific application, we do have a limited number of options when you start getting into a rotating system. Big torque measurements. What do I need to know about high capacity torque measurements? Well, one thing that comes up in many cases is that the higher capacity torque measurements in many cases are low-ish RPM, maybe not rotating particularly fast or through many rotations. And in that case, a reaction torque sensor starts to become attractive because large rotating sensors with bearings and things start to become quite expensive, and also they're just not as necessary. Again, if it does rotate through multiple rotations, though, a rotating sensor is required. Typically, Interface provides sensors up to about 100,000 inch-pounds in the rotary type, and that would be a flange style sensor or shaft style, and then above that they become shaft style sensors. Again, large torque measurements also maybe sometimes makes more sense to do it with a load cell. That would be some kind of a torque reaction measurement as opposed to an actual torque measurement. I'm going to ask Chris if he has any more comments on this one.
Well, it's somewhat not sure if the question is specifically related to rotating torque or if it's relating to reaction torque. But one comment I would make is when you're talking about rotating torque specifically, the larger capacity that we're looking to measure, generally speaking, when you're dealing with a torque sensor that uses a bearing-supported rotating shaft, otherwise one of our inline rotaries, the cost for the larger torque sensors rises fairly significantly, and so in large torque applications, oftentimes a more economical approach to making this measurement is to use products such as our HRDT telemetry-based torque sensor. They tend to be a more economical way to measure rotating torque in large capacities, so certainly something to keep in mind.
Thank you, Chris. Moving on, what will be the uncertainty budgets for the torque calibration or torque transducer comparison calibration? That's a big question. I don't know that I can actually address that here, but we do torque transducer comparison calibrations in our lab, and we are accredited to ISO 17025 by A2A. And what I did bring to this discussion is a copy of our accreditation, which does show uncertainties for torque comparison calibration. So we do have a full ability to calculate the associated uncertainty with any of the torque calibrations that we perform. There's lots of factors that go into that are very lab and equipment specific, though, so it's hard to get into that in generalities, except to show that we do have various different ranges of torque, and some of those are ranges on a given machine. Some of the, at some point it jumps to different machines, and those systems have different uncertainties associated with them. So, for example, in the comparison system, we have 3 different ranges, and they have 3 different uncertainties. And again, the uncertainty is a worst case. So in this case, the 0.11% uncertainty would apply to the 1,700 inch-pound point. And then at 10,000 pounds, it would be proportionately lower uncertainty. So the uncertainty is worst case at the lowest point or applied point in a certain range. So you see we have 3 different ranges there, all done with comparisons. So I hope that at least somewhat answers the question. If we had specific questions about how the calculations are performed, we could address that offline. Back to the PowerPoint. This is a good one. I really don't know how to answer this one, but I'm going to give it a shot. If the torque spec is 90 Newton meters plus 60 minus 75 degrees, what fastening application would be best? Torque and angle or angle and torque? I'm assuming when you say 90 Newton meters plus 60 minus 75, what we mean is to apply 90 Newton meters and then continue 60 more degrees, and then back off by 75 degrees, and that's, you end up with, whatever you end up with after that condition. Would you agree with that, Chris?
Keith, I think reading this, I think the way I interpret this is, and this is pretty typical in fastener torque measurements. What they use is the torque is actually essentially for like critical joint measurements. So you typically use torque to as almost as a trigger or a threshold, meaning you have to achieve 90 Newton meters here. But then once, I think the 60, it's not 60 plus 60 minus 75. I think it should be reading plus 60 to 75. So in other words, once they hit 90 Newton meters, they want the torque to, basically they want to apply another 60 to 75 degrees of rotation. I think that's what this is referring to.
That makes more sense, and I think I would agree that makes more sense than backing it off 75. But in any case, we could measure that using several of our sensors or sensor instrument combinations have torque measurement and then degree measurement as separate channels. So you can basically measure torque and angle separately but simultaneously, and you could achieve any combination of Newton meter and torque. That would be a manual system, though. We're using a torque transducer to monitor both the torque and the angle as the torque is applied. The question leads me to believe that there are certain other systems in the market that would, say, have certain modes for measuring this. Maybe they're automated, or they do some kind of analysis of the data, and maybe there's a torque and angle or angle and torque mode or different equipment. But we sell basically the components for measuring torque, and then instrumentation that measures torque and maybe logs it or displays it as a graph along with angle and whatnot. But we don't necessarily have anything specific that really does the testing. So I can't really address that part of it.
I basically, Keith, you're exactly right. I mean, there are a variety of suppliers that supply basically automated fastening equipment, and if you're applying a torque to a cylinder head bolt, for example, the specification is defined as a torque plus a certain degree of rotation, and it is an automated feature. It really, we would, potentially offer equipment that could be used to check or validate the accuracy of that type of equipment, but we don't have the functionality of being able to do positive torque and angle or angle and torque control.
All right, I think Chris and I both are interested in these types of applications, so again, maybe offline we could discuss this further with anybody who's interested and understand, because we might be interested in offering something that could address this type of application if we understood it better. Next question, why does the metrology community, specific to torque measurement, not properly estimate the associated uncertainty with the measurement being made? That's a tricky question. I think some people in the metrology community do estimate it properly. I think Interface does on the systems that we use in our lab to calibrate other devices. I think in many cases, equipment may have a lot of uncertainty associated with it that isn't accounted for, such as geometry of the loading and couplings and things. So I think it may be that those are difficult to account for, and so they're ignored. Maybe that's the easy way to deal with things, but not the correct way. Any comments on this one, Chris?
No, I really don't, Keith. Other than, I guess I'm in agreement with what you just noted. I don't know what specific factors that that this question referred to in terms of being overlooked or misapplied. But yeah, that would, again, I think this would be one if you got some, if this is something you would like to discuss in greater detail, feel free to give Keith or myself a call and contact us offline, and we'll certainly work with our engineering and quality people to make sure that you get an answer that makes that satisfies your question.
We're at 30 minutes. Okay, good. Yeah, we would like to understand this better. Interface makes and has been involved in the metrology measurement area in a long time with our gold standard load cells and calibration equipment, and we also make transfer standard torque sensors, and so we're getting more into the sort of calibration side of torque and offering standards for people who use them to calibrate their own, torsion machines such as torque wrench calibrators and whatnot. But we would definitely like to understand more about what the challenges are facing that community. I do know NIST doesn't support torque, which is somewhat challenging, and so maybe there's not quite as much resources here in the U.S. as there are in other countries for torque measurement and then associated uncertainty calculations and things. Moving on, what adapters do you use to hold the torque wheel to the transducer center line? This is a tough one, so I'm not sure exactly what is meant by the torque wheel, but I can comment somewhat on square connections. Just as we talked about, say, with shrink disc type couplings that apply a torsion uniformly around the sensor shaft versus a key that applies a point load at the key, unless it's a interference fit, but just a slip fit with the key, the torque is actually applied as a force at the keyway. On square fittings, you have the same issue, except the squares are typically quite a bit sloppier than a hub sliding onto a shaft, and you have potentially 4 points of engagement that may move around as the torque is applied, even in a system that fits well as things bend and mate together with increasing torque. So even the best square connection is less than ideal. And then as you get into sloppier connections, they can have a significant effect as the torque application, or I should say the force application point, moves around on the square. So you imagine if you're applying the torque right at the very corner of the square, you can get a different amount of torque than if that same force is transmitted further down the side of the square. So I think that may be one of the sort of inherent problems with square type connections. Do you have any more comments on that one, Chris?
Yeah, square drive torque sensors in general, they are notoriously known for poor fit. Basically, it's a necessity, virtually a necessity, when you're going to be changing out tool sockets and other other tooling that's going to interact with the square drive. It's sort of an accepted, I guess I'll say an accepted compromise that must be made when using a square drive sensor. I don't really know how there's any way for a production tool environment to utilize a square drive with any higher degree of tolerance than what's already there.
All right, next question. What can I do to reduce my uncertainty, and how do you correct these issues? I think that's a related question, and again, that's been addressed, and that it may not be real easy to do with a square connection. This is another tricky one. A lot of metrology questions today, which is good. I'm not going to actually read this entire question, but to address it, we're doing a torque wrench calibration. Interface does not calibrate torque wrenches. In fact, we send our torque wrenches out to a local shop to get calibrated. That said, we are involved in the metrology side of torque measurement and do offer torque transducers that are used to basically check or calibrate machines that are used for torque calibration or torque wrench calibration. And also we can offer sensors that have, say, square drives that could be used to check a torque wrench. As far as the actual procedures for doing the work, though, we do not really get into that, so I can't really talk to it with any level of intelligence, but I would like to say this is something we're more, we're interested in getting more involved with, especially as we start to deal more with the metrology side of in traceability chain of keeping the torque machines in the field in calibration with, so by supplying sensors for that purpose, you'd understand these issues that customers are dealing with. So we'd like to maybe understand this one a little better by discussing this offline as well. So Dale, hopefully we can discuss this in further detail separately. What are the largest contributors in an uncertainty for a torque calibration? I think in many cases it's the actual application of the torque. And so if you're actually, say, calibrating a torque sensor, you can either do a comparison test where you're applying a torque to both sensors simultaneously and comparing the output of the device under test with the calibration standard torque sensor. In many cases with torque, the load is applied using dead weight on an arm. That dead weight on the arm can be used also as the torque reference, by calculation of the arm length and the applied weight, or you can just apply the load using that and then I'll just do a comparison calibration. So you're just using that method to apply the weight, but not necessarily to measure the applied torque. But in any case, there's a lot of variability in how that can be accomplished. When you have the two sensors in line for a comparison calibration, there's the assumption that they're both seeing exactly the same torque. If you're, say, not using appropriate couplings, then you may have a lot of bending or other extraneous loading in the system that really prevents the torque from being identical and the two devices under test. And in torsion, that's more difficult than in, say, forced calibration. So I think it's one of the bigger factors, but it's not necessarily well understood. Another thing was if you're using moment arms, again, you can have a calculation of the applied torque, but if that arm is bolted directly to the sensor, there's also a lot of overhung moment applied to the sensor. And so that can adversely affect the output of the sensor. And so you think you're applying torsion, but you're really applying an increasing torsion along with an increasing bending. And so in the application, if the customer or the user doesn't have any bending, then you've really calibrated it in a condition under which it's not going to be used. We see that a lot with test machines, where the test machine is a torsion test machine that's applying a true torsion to a specimen, but to calibrate it, instead of using the calibrated torque sensor and trusting that, the end user puts a weight, puts an arm and a weight into the system, and then they've got a giant amount of bending in the system. They basically calibrate everything using that method, then you pull that out, remove the bending, and then start doing your testing. And really you've basically calibrated the system to a different condition than it'll be used. So you get very significant amounts of error and uncertainty from those types of conditions. They can be addressed, by understanding them and then dealing with them. For example, with overhung moment during calibration, you can move the weights around instead of adding weight, which keeps the moment constant, for example. So there's various ways to do that to accomplish, or sort of minimize the uncertainty. But I think that's not well understood in many cases, so it's, I think, the biggest contributor. Do you have any comments on this one, Chris?
Well, pretty much I think you hit on the majority of them, Keith. As I, in the field, whether it be at our factory or in the field, by far and away the most common method for calibrating a torque sensor is through the application of a moment arm and dead weights. And the dead weights are typically certified by a governing body and are traceable. The calibration arm very often is less tightly controlled in terms of the actual overall length of the arm is sometimes at question, and getting the arm length certified to match the precision of the weights is oftentimes ignored in the field. Also, when the torque is applied to the moment arm, you have torsional windup of the torque sensor when the load is applied. This allows the moment arm to rotate, and if the load is applied while the moment arm is at some angle other than perpendicular and level, you introduce some errors into the torque measurement that are typically accounted for by using a gearbox and a leveling mechanism and a bubble level to bring the moment arm back to level after applying the load. The problem here is that the bubble level is typically applied at the center line of the device under test, and this ignores the fact that the moment arm itself can deflect over its length. It can be level at the moment the torque sensor at the center of rotation of the torque sensor, but as it moves outboard on the cal arm, that deflection needs to be monitored as well. So big error potentially is a moment arm that doesn't have adequate stiffness to prevent deflection over its length.
Good answer, Chris. Moving on, aside from a more compact format, is there any reason to use a torque transducer over a load cell at a known offset? Yes. In many cases, the load cell is less expensive, so that's a good reason. In some cases, you can get better accuracy, or at least every bit as good of accuracy. The downside is that in packaging, really, it's kind of easy to understand how you could measure torque using a torque sensor. To do the same using a load cell, you have to somehow apply or react a force at a distance off center, which, say, on certain situations is quite easy if the device is, say, gimbaled. And I have a picture I can show you of a dynamometer that actually uses that scheme. Whoops. Here we go. So this is a case of a dyno. Instead of using an inline torque sensor, it uses a load cell off center. And this is a great way to do it. This is an eddy current dynamometer, though, that is gimbaled at its center line, basically, to allow this. If it were, say, an AC motor bolted to a plate, it's very difficult to gimbal that system. So sometimes it's the geometry of the items involved in the test that really dictate whether you can use a load cell or you have to stick with a torque sensor. Any more comments on that one, Chris?
Issue of Keith, the only other comment I would have would be when you're dealing with applications requiring dynamic frequency response, the use of a load cell like you showed in the Attendees dyno can have a much more damped response characteristic than an inline torque sensor would. So if you're looking to measure transient loads, transient torques, cogging torques, gear meshes, things like this, where frequency response is critical, an inline torque sensor is definitely going to have the potential to provide you with better service.
Yeah, good point, Chris. To expand on that a little further, I think as well as with force measurement, the idea is to get the measurement basically as close to what you're trying to measure as possible. So like say on a load cell system, if you have say a bearing or a pivot or something, you'd want to you wouldn't want to measure through the pivot, for example. So same thing with torque. The inline sensor can get the torque sensor right as close as possible to what you're trying to measure. If you kind of scheme up some system where you react the load using load cells, you may end up having the load cell quite a bit removed through a number of joints and pieces away from what you're trying to measure. So all of those have effect and influence on the measurement. So as close as you can get the sensor to what you're trying to measure usually is the better. Let's see. This is a tough one. Measurement of torque on an 8-inch drive shaft is needed. So the question is, on these kind of applications, is the customer able to cut the shaft? And in many cases, the answer is no, because the thing doesn't work once you cut the shaft, and the torque sensors don't necessarily mate into the system very well. So that's the first question, and let's assume that yes, they could cut the shaft, and then modify the shaft so that a torque sensor could be mounted in line. Something like this is still difficult because it has to be protected from the elements and allowed to spin freely. Like you say, slip rings wouldn't be good, nor usually a telemetry system that's close coupled doesn't work very well because of the gap changes as the drive shaft moves around. Battery-powered telemetry sometimes is quite useful in these types of situations. So there are typically certain reaction-type torque sensors that could be coupled in, but then a battery-powered telemetry system can be added, and that basically broadcasts the data without requiring a closely coupled induction power transfer system. Other cases, the sensor or the shaft just has to be strain gauged and telemetry is applied. Interface doesn't get into strain gauging of shafts. We have a limited ability to provide battery-powered induction systems. So it's something we could talk about, but typically these are difficult applications that I don't necessarily have a great answer for. Okay. Moving on, we do not have any facilities for doing testing. We supply the components only. So we can certainly provide torque sensors and instrumentation that would allow somebody to do the testing, but we do not do the testing here. Is there any protection in case the torque goes over expected capacity? Certain torque sensors have overload protection built in, and that would be a mechanical stop that protects them. Those are typically lower capacity reaction style sensors. We also have dual range sensors that allow, say, a high overload, but also measuring at a very low range using the second range. Those have their limitations though, and they're not necessarily as good as using a low capacity sensor to make the low capacity measurement, but they do allow survival of the higher torques. Next question, difference between a rotary and reaction torque sensor. A reaction torque sensor is basically a strain gauged element that reacts to torque. If you spin it, you have trouble with the cable wrapping up. So rotary sensor basically just adds extra things to that reaction sensor. It allows it to rotate without the cable being soldered to it. How do you ensure that the torque sensor is installed on center? That goes to uncertainty and slippage, and you want to make sure the torque is applied through the center of the sensor. And in most cases, the torque sensor actually has a feature that is dedicated or intended specifically for that purpose, a boss or a pilot. And so usually if you look at a torque sensor, there is some feature that is tightly toleranced that's intended to be used for centering. Finally, what type of couplings do you recommend? We like disc type couplings. They are positive engagement, zero backlash. They are relatively soft in the directions you want them to be soft, but they're very stiff in the torsion direction. Bellows couplings, which are shown on the right, are also okay, not as recommended as a disc type coupling, but they can be quite soft, which is usually desirable. Things like gear couplings are not recommended. Universal joints, all of those types of couplings tend to have undesirable characteristics for torque measurement. Universal joints can apply a lot of extraneous loading as they rotate, so you need to take extra care to protect the torque sensor when using something like that. A gear coupling can provide a lot of thrust loading under torsion, and they don't mesh cleanly, so you have vibration and things to deal with in the measurement. So those are less desirable as well. In fact, gear couplings we quite pointedly do not recommend.
We do have a question from the field. When testing a torque wrench, if it reads low on the low end and high on the high end, can this be calibrated or repaired? Does it need a new spring?
That's a good question, and it's interesting that we're getting a lot of questions about torque wrench related type applications. We do not do torque wrench calibration here though, and I honestly cannot answer that question. May depend on the brand or the manufacturer of the torque wrench.
Okay, it looks like we've got all the questions answered. If you do have a follow-up question you think of after the webinar, go ahead and email those to goto@interfaceforce.com. That's GOTO@interfaceforce.com. If your question stumped our experts, please expect a follow-up email or phone call from us in the next week. I want to thank you all for joining us. And I hope you all have a happy Wednesday and a happy holiday. We should be doing one more webinar before the end of the year, so stay tuned for that. Have a great day.